you see relations afterwards? I didn't get what you know.
Yeah, no. So I didn't say anything about integration. In fact, I only know about integration in the UV limit for very particular integrals where for n equals 4 and n equals 8, you actually have the same integrals appearing with the same coefficients. Exactly the same integrals for the UV divergence in the critical dimension. But that's all I know about integration. I think, and so I should also make the point that in general, as you're considering quantum corrections to classical solutions, right, you shouldn't expect a squaring relation or any sort of obvious squaring relation because you're talking about something that happens after integration, not before integration.
Any other comments or questions on the presentation or related material?
You were going to explain about the UV completion?
Oh, I was going to explain. I have some comments that there's a cute story about the amount of structure in string theory. Obviously, KLT relations, holds perturbatively. But you can ask if there's any role for Jacobi relations, on the open strings. And there are a couple of cute stories. One is Stefan Stieberger and Tommy Taylor. I guess it was a couple years ago. Put out a really provocative paper where they made a claim saying that open strings were related to supergravity amplitudes at tree level. And it sounded really weird when you open it up. It looked even weirder. But this was clarified by Stefan and his collaborators Carlos Mafra, Oliver Schlauderer, and Johannes Brodel, where they showed that open string tree level scattering amplitudes of a given permutation, right, of color ordered open string tree level scattering amplitudes were given in terms of functions of alpha prime dotted in with the KLT matrix and open some n-3 factorial basis in gauge theory tree level. So I wrote this vector, this n-3 factorial vector of color ordered field theory, scattering amplitudes. These guys, so this is the classical KLT. So this is a low energy limit of KLT. This is all orders of alpha prime. And this has a basis in n-3 factorial, and it obeys exactly the same relations as this does. And in a sense, this is a transform. This all orders in alpha prime is a transform of color ordered partial amplitudes. The fact that it takes this form actually means that you can write these guys as a sum over cubic graphs. This isn't something I stressed in my paper, but it's true. Little zi of G and of G. So where this is tracking the permutation of this. And then,
Are the propagators only massless ones?
Oh yeah, massless propagators. Although these are normal, the whole alpha prime, yada yada yada. So, what do I have to say? Okay, the first thing I have to say about UV completion is, of course, this works for n equals 8, which is possibly UV. But the second thing is that these structures do seem to appear in string theory. In fact, this latest very cool calculation by Oliver Schlauderer
and Carlos Mafra of 2-loop, 5-point string scattering, right? So genus 2, 5-point string scattering. In their appendix, they actually checked that the BRST invariants they're building the quantity out of obey Jacobi relations. And so that's, so if you're interested in looking at this structure on into UV completions, that's possibly one place to look and some people to talk to. That's all I have to say about UV completions.
Actually, another thing, maybe while you're up there, so you raised this question of, let's do something else pressing. You raised this question of whether we can get the solutions from the amplitudes, or well, various people raised that question, but you amplified on that. And there was this brief description I gave of, for example, what Duff had done and the possibility of generalizing that. So there you basically put in a source and then you attach tree diagrams in all possible ways, and then you generate the classical solution. So you might think you are pretty close with the amplitudes to having a fairly general classical solution that way. But the question is, what are the challenges there? Obviously, it's not.
Yeah, besides bookkeeping.
Yeah. Well, right. Yeah, but it seems like in principle, maybe that's a way to exploit the double copy structure directly. And see how to get more general solutions in relation to the double copy structure.
Yeah.
So,
no,
anything else? If anyone here has other thoughts on that.
I mean, there's a trivial relation which I think goes back to Padea, which just follows from that summing up the same graphs. I mean, I haven't seen these explicitly, but it's just a statement that if you expand the classical solution in the powers of a linear one, there's a relation between that and the estimators.
Exactly. Yeah. Right. Yeah, I think that's basically what's being
so the nth derivative of the nonlinear field with respect to the linear field is the n part of estimators.
Yeah. Yeah. So the Feynman diagrams are giving, in other words, solutions to the equation to motion.
That's a good question. Presumably, yes. Yeah. The question is boundary condition.
If you use retarded promulgators, you get this Dyson mess with double graphs.
Oh, okay. Yeah. You know, reference. I'm trying to figure out where I learned this from. For this work with the data, but you know, are there other references?
Of what you just said?
Yeah.
I didn't know if it was this. I think you know it.
I think we got it from today. I didn't remember
I think I learned it from your paper. And then the reference to.
I think there's a reference there.
Anyway, this seems like a kind of obvious direct route to generating much more general solutions, but maybe there are some, practice obstacles, or I don't know whether they're in principle.
There's presumably a limit in this formula. You're taking n derivatives, you want to get a scattering amplitude. You usually need to take a limit that's going to put some, it has to be on shell.
Right. Yeah, the linearized solution is on shell, so it may not. It's not clear how generous that it would be. It will give you all classical solutions, as I'm saying, ones that satisfy Feynman boundary conditions.
Well, there's a really bad way. What you do is, let's say you have scattering amplitudes, you can always work backwards and construct a Lagrange.
I agree.
Of course, as I said, it's a really bad way. But at least it shows in principle that the information is there.
But again, literally, that's basically what Duff did in this example. Point mass and add up, whatever compares. Everyone knows the diagram.
That's a scattering amplitude with an extra particle in the theory. You have to add this massive particle.
Well, you have a source. No, well,
justify a tree approximation.
Absolutely.
You're attaching sources to trees, basically, like this series.
So, then the equivalent, as you pointed out,
was in the scattering process is to take a high energy solution.
Well, yeah, you
Because
expect
then
this
the
to
high
build up.
energetic particles act as sources.
Yeah, you expect this if T, the source is the stress tensor of a point mass sitting there. Duff showed you get Schwarzschild. If you have instead sources of colliding particles, you expect to build up the metric of the collision geometry, I think.
Much more
By the same token, which is much more complicated. But
only at large impact parameters, you know, the different
that's where we really are.
shock waves, otherwise.
Yeah, we best understand it, but still, and of course this, for a general source, is horrendously complicated, but it seems like at least there's a fair amount of simplification as compared to the general story that occurs because of the nice control of the tree diagrams that you guys seem to have. How much does that help? That hasn't been, it sounds like it was pursued directly.
Well, how many sources are reasonable?
Well,
I mean, sources could have a lot of parameters.
yeah, no, but for example, you might show that you get, even for a general source, something like a double copy gravity solution via this kind of construction. Something that is, like a Yang-Mills squared relation. Because all the amplitudes have that form. Of course, the sources, I guess, won't necessarily factorize, but.
I think the thing to do would be to choose what we find a gauge, or things like that. So we don't, in the Duff calculation, we use these Kershel coordinates. It's linear. So the calculation stops at the first order, you're done.
Yeah.
You just have d squared h of j. J is delta. But now if you have something more, you got some more complicated stuff coming in, probably you don't have to use Kershel coordinates available, and that's one of the tricky things. I mean, I think what we're learning from the amplitude story is that there are gauges where these calculations become very straightforward, but we don't really know what the gauges are. I mean, that's, in a nutshell, that's the problem with the food level. You're trying to find nice new ways. You need to go to this gauge, don't know how to do it. It's hard.
Well, it's kind of it was rather surprising to learn that the Schwarzschild solution was a solution of a linear equation.
I don't know why we're not taught that as undergraduates.
That would only confuse us.
There's 1 over r, the solution of Newton's equation sitting right there in the metric. Yeah.
I mean, not just Schwarzschild curve. I mean, it's not just Schwarzschild curve. And I mean, Ted Newman had this lovely way of going from that representation to displace the Schwarzschild into the complex of it to get the curve solution. Just a linear superposition between Schwarzschilds. One, and it's Schwarzschild and its conjugate displaced into the complex.
So, but surely that is, that's kind of exceptional.
Yeah, but it's one of the, this is the most important solution, isn't it? Apart from flat space.
What about unstable black brains in higher dimensions? Something like that.
That will be the obvious next generalization. What we could imagine.
ADS Schwarzschild is also Kershel.
Really?
What about this center?
It's just got an good question. I don't know. I've been asked that many times. Yeah, instead of having either been used, you put the two anywhere.
So ADS also has?
The metric is ADS plus basically KU 1 over all.
Well, I guess the question of what.
Oh, I see.
ADS expanded around
ADS is not Kershel around the class.
I think the kind of metric black holes, at least many of them are Kershel, and that's how the Evans guys discovered them was to use the Kershel concept.
If some black hole, or even some pseudo black holes are Kershel, don't the near horizon geometries also have to be Kershel?
Well, it sounds like it, doesn't it?
Yeah.
you're saying 80 is curve field around.
Yeah, so, yeah. Much more complicated solution called resonance-Nordstrom.
Resonance-Nordstrom is interesting from this point of view, because it's a double copy, it should be asymmetric. It's supposed to be, like, the relevant scattering amplitude would be a copy of Yang-Mills times Yang-Mills of the scalar. So
And you have found that?
I don't know how to make we're working on it.
Oh, okay.
It's not anything.
So I'm not sure you can then continue to do this trivially and exclusionary of physical behaviors.
Well, you use the fact that you have a null vector, right? So,
You know, who said we have to have physical gauge theory solutions? I mean, to do a double copy decisions.
Oh, you say it's a solution generating.
Yeah, just as a technique.
Yeah, that's right, actually. Yeah. It's the boundary conditions we're willing to accept for gravity quite different from the boundary conditions that seem sensible.
Has there been any work on, is there anything like gravity is gauge squared with conformal gravity?
Yeah, I don't know. I mean, you know, so you see these things in the vertex operators, the relevant string theories, but of course, it's not good. The only way I know how to be conformal gravity is in twistor space. And one of the real peculiarities there is that
No, sorry, I mean, maybe just to, presumably, such a relation would involve squaring the denominators, but.
oh, you do want to square the denominators?
Definitely.
I see.
Otherwise it's not.
Yeah. No, I see what you're saying.
Yeah.
It could be that the Yang-Mills is squared denominators as well.
Sorry?
The Yang-Mills can have higher denominators too. The gauge.
Can you do this for Euclidean number?
Well, these things are signature independent, aren't they?
Yeah.
I mean, the basic idea is all analytic and momentum space. And,
So, what about the Schwarzschild?
The equations are still the same equations, right? So.
But you need, K needs to be null, so you have to complexify or something? You have complex solutions in Euclidean?
Yeah.
I wanted to ask about the perturbative finiteness. So we seem to mostly have believers here. What I always heard before was, oh yeah, it's finite, but at 9 loops it will diverge and so on. But then many people here seem to have a lot of faith that it will keep on being finite. I understand there's some computations that will shed light on that, perhaps in 5 dimensions.
Well, it's, yeah, I mean, I don't know what part I should talk about, but so people certainly have many beliefs on this. People have been thinking about this for a long time. In my mind, the important question is not what we believe, but what we can calculate and what we know. And I think the first part about, like, does it diverge? The way I would say it is just an open question. And anyone who has made predictions about where specific divergences exist has routinely been wrong year after year. Of course, that doesn't necessarily mean that the future will be the same. But what was the other part?
Well, I understood that the naive expectation for where things might diverge for maximal supergravity in 4 dimensions is at some fairly high number of loops.
It's a high.
But that same logic would tell you that in 5 dimensions you'll get a divergence at 5 loops or something.
I guess you're asking, is this a decidable question? That's what you're asking.
Yeah, I thought there was going to be some new data points.
In fact, there is already data points on exactly where people predicted the divergence. So, yeah, maybe this is my talk. I'm talking about it. I spoke, but anyway.
Yeah.
So the way you can get new data is by lowering the supersymmetry, which is what we've done. And you use the double copy construction. When one copy Yang-Mills, the other supersymmetric Yang-Mills, you do anything for supergravity. If you look at the places where there should be divergences, they're in fact not there at the first level. Now, of course, what we want is to understand the mechanism that's behind it. In fact, the question I see is, do we care if it's perturbatively finite? That, you can either care or not care. I don't think that's the important question.
Well,
I think the important question is
we'll come back to
why.
that.
If
Well,
it's finite, why is it finite?
Yeah,
I
then,
think
okay.
that's the important question. Because then it's not an accident and it's clearly very deep.
You advanced a conjecture as to why it might be finite, which you didn't reiterate now, but let me reiterate it and see if I understand it. You said that even if you look at non-supersymmetric gravity, the one-move divergence there is really a consequence of an anomaly.
Right.
And therefore, in some sense, if there were no anomalies,
Right.
and I did say gravity is not going to have one, it should be finite.
Right.
And if there were anomalies, non-supersymmetric gravity, the word also is finite.
Yeah.
That's a very strong.
That is a very strong statement.
It's
One
would
But
explain.
then what would that tell you about the what prediction would that make in the 5-dimensional maximum supergravity? That would also be perturbatively finite?
No, 5-dimensional is going to diverge. You can forget about that.
The formula is 4 plus 6 over L, where L is the number of moves. So that's where it diverges.
It's certainly against the pure supergravities. Every example, which means two examples, only two examples we have of divergences. Both of those cases, to our great surprise, seem to be special. The divergences you find, they do look like they're tied to anomalies. Now, the reason why I didn't push that is because you may ask me the next question, which is, name the anomaly. Tell me which one it is.
The burn anomaly.
That'll take more time to find.
But can I ask this, and this is talking personally. So for n equals 8, so far, there's no miracles, right? I mean, in the sense that things are a consequence of E7 symmetry.
Well,
The data,
the explicit data.
I know there's other indications of magic, but I mean, just purely the explicit data. Now, for these lesser symmetric examples, are there any symmetry explanations for what you found, or no?
There are no symmetry. People have tried.
So, but people tried that. People tried before as well with these highly dubious representation-dependent formalisms. Instead of doing something at the level of trying to write down an amplitude with the correct symmetry properties, then people made much more robust statements when they tried to write down the amplitudes with the correct vanishing limits. Have people attempted that exercise?
People have attempted, people have attempted, but not very hard. So there's no papers describing it. So I guess you're probably referring to the finiteness of n equals 4 supergravity at 3 loops.
Yeah.
There have been papers, actually there's a lot of paper written on it, like 120 pages.
But the problem with all those things, as well as the n equals 8 things before, there are more statements about the formalism that people are using than anything in variable.
That's right.
Right? Whereas that's why we made, not we,
That's
Paul,
right.
Henriette, and Nicholas had already progressed by trying to just write down an amplitude. That's correct. But I'm just asking whether they attempt to do this.
There have been, I think people have looked at it, but nothing has been published, and my guess is it's not going to work again.
I see. Well, that would be very striking.
Yes. But there's definitely a puzzle. So one of the conclusions of my talk was there's a puzzle to be explained, and I welcome those who work on these things to try to find an explanation, a conventional explanation. I think my own feeling is this time around it's going to be very hard.
What's the symmetry? Sorry, what's the symmetry? What's the symmetry of the n equals 4 here? What's the analog of E7 for the n equals 4?
Well, it's an SU11. That actually has an anomaly in it. There's a U1 subgroup that's anomalous, and we believe that it's that anomaly and related things that are the cause of the for loop divergence in that theory.
And the for loop has been shown to be different?
We calculated it, it diverges for sure. But that's if you use the SU4 formulation. Yeah, so it definitely diverges. But it has a funny structure. I didn't really discuss it, but it has a funny structure that makes us confident that it has to do with anomalies.
So there's something about this whole idea that these theories could be finite that I've always found very puzzling, which is it's certainly true by counting the graphs, and I don't think anybody is claiming that the perturbation series converges. And so since the perturbation series is a series in powers of momentum divided by Planck scale, that implies some kind of funny singularities at momentum invariance equal to 0. And I don't understand what the physics of the, because it's a divergent series around momentum equals 0. And so that implies exponential.
There are, of course, many theories we know and love that have QCD.
But those are series in a dimensionless coupling constant,
Right.
not in powers of momentum.
Why do you say it's momentum? Why do you say?
Because the expansion parameter is ST
What I believe is
U over n Planck squared.
So it's no momentum, it's okay.
No, but Tom is saying that
Well, he's saying that order behavior perturbations.
n Planck squared over e to the minus s over n Planck squared. E to the minus n Planck, yeah.
It's not a convergent perturbation series.
And it's not even asymptotic if you're high energy, since we were discussing.
Well, let's stick to
But all of these things do diverge at
Okay.
as the phase goes.
Not these crazy divergences. These are not divergences that look like, infrared divergences
Yeah, yeah.
of gravitons being emitted.
But you're asking what happens when external p's go to 0?
Yeah.
And then you're worried about n factorial p over n to the n
Right,
behavior.
which leads to
Which
singularities
might-
of the type that can't
might-
come out of infrared
might-
divergences.
might.
I mean, we know what the infrared divergent structure of gravity is.
Yeah.
So,
Not to all orders,
what?
do we?
Yeah,
Well,
calculate your
but you have to-
favorite
but you have-
quantum inclusive
But have to
cross-section.
combine that with the center expansion. So.
This is just an expansion in P. Take a Bloch-Nortzig inclusive cross-section. According to this, it's got an asymptotic expansion in the invariance over the Planck mass. It's totally finite to all orders in perturbation theory, and the perturbation series has an n factorial divergence in the n loop order.
But not the infrared singular.
But it's not infrared singular at all.
You
So
see,
it has
Tom, let me give you a little model for
Sorry.
various things might be. Okay. So if you take a little, this is just if you just take a classical model for black hole formation, where you just have a spherical shell and it's collapsing. Then if you just work out the particle mechanics for it, it just looks like potential that runs off like this. But you can tunnel, I don't know what it's called, but when you bounce off as a quantum phenomenon, when you instead of rolling down, when you bounce off, whatever it's called, you get something that goes like e to the minus. You get an amplitude for that goes roughly like e to the minus the entropy of the black hole that you would make.
Yeah, sure.
So for
No,
I know, but I'm saying, and what I'm talking about, of course, quantum mass is much bigger than the Planck scale, which is not what we're talking about.
Yeah.
But I'm saying that there might be a continuation of that phenomenon, which is at arbitrarily low energies, some gravitational amplitude to bounce back.
Anyway, it's not at all, why is it clear, by the way, that this thing diverges in factorial fashion?
Just counting pi.
Yeah, they're arguing. They're arguing.
Okay, so is the conjecture that the perturbation, the finite order by order perturbation series also converges? and has some singularities
All
and some
the-
finite
all these
momentum
relations
according to the
for
Planck mass.
So planar QCD is another finite theory,
Yep.
which doesn't have this problem.
Well, it's got renormal singularities, but
Not n equals
not n
4.
equals 4.
Yeah, so that's the finite one.
Right.
The others are,
Yeah.
I mean, this theory, if it's sort of normalizable,
Yeah.
it's finite. It's more like n equals 4.
Yeah, yeah.
The
Fine.
Mills theory.
Fine.
And there we know there are things that are described by convergent layers theories.
But only in the planar limit. There are either the
The
minus
planar.
n corrections to the planar expansion.
Well, the non-planar is, of course, also planar.
Yeah, but there are,
Everything
but
is finite.
but the perturbation series is not convergent.
Right,
Well,
the
do we
link-
actually know that?
What?
The layers, that the super.
For QCD, yes, we know it.
For QCD, of course we know,
Okay.
but for supersymmetric angles.
You mean that it's not convergent?
Yeah,
No.
so n equals 4 because there are instantons that you can calculate. Right? Instantons were just an SU2 subgroup of the gauge group that has an instanton in it. That gives an e to the minus n.
But how do you know what the structure, I don't mean the defining diagram counting. If there's anything we've learned, that counting is not correct. If you want to scale anything from looking at how the diagrams.
If you look at, the path integral formulation, it looks like it's got essential similarities in it. Right? Everything indicates that. It's true in every quantum theory that we know.
But what we're trying to say, plain and simple, is there's a new phenomenon going on that's happening between diagrams. In fact, maybe you didn't come to my talk, but if you look at any single diagram, it behaves poorly, and that we can prove.
Right.
Okay? And we can prove that the basic statement is that if you allow the diagram, or you only allow Feynman propagators, then you can prove that some order of perturbation theory is in fact that 7 loops, where in n equals 8 supergravity, you will find divergent diagrams. Right? But the idea is the combination of the diagrams. And this is in fact exactly what we see in n equals 4 supergravity or n equals 5 supergravity, that each diagram is poorly behaved. So if you're going to make any argument you try to construct, you can't do it generically. You can't say, well, we generically know how the diagrams behave. We generically know how the counting goes.
So
it's very
specific. Is your claim that the perturbation series, which, let's take it that it's finite order by order and all orders, you also claim that convergence.
I do not claim that.
That it's analytic.
I do not claim that. I do not, any more than I would claim that for non-planar n equals 4 super Yang mills. I won't claim it there, and I won't claim it here.
But Tom, once again, I don't see what's so bad about e to the minus n Planck squared over s. I mean, if you call one over s r squared, it's like e to the minus n Planck squared r squared. Those are exactly the things that we expect are there, right? Those are. It's just that we're sort of continuing it to a region where s is very small. It's true.
Yeah,
but
I don't see the physics, Ema. I mean, every example I know of that kind of divergence, there's a nice, simple physical explanation of what the divergence comes from. There's instanton, there's a Dyson-type argument that explains what's going on. In every example.
But look, lack of understanding is not an argument one way or the other.
Well, but there are indications, clearly, that there are very profound non-perturbative puzzles, and there are various ways of seeing how you approach them. And so it seems like the big question is whether the structure that one is finding in perturbative expansion is going to help with that or not. And so if it doesn't, then we've still got more profound problems to deal with.
Turn around what he's saying. Let's suppose that it's funny. And we understand the reason why it's funny. Right? In some detail, it's a symmetry, it's some.
Yeah, if there's some symmetry you discover, then maybe that will save us.
Then I would be shocked if it would not have non-perturbative implications. Basically the reason you're saying.
Yeah, but something.
So in the sense, you know, what we're arguing, it's where you put the weight, right? You're putting the weight, you have a non-perturbative well, and therefore, you're gonna make implications about the perturbative. I'm going the other way. I said, I understand the perturbative well, I see something happening here. But I think we agree at the end there's gonna be, these two are connected. But we can't, unfortunately, I can't say more because you have to understand the underlying reason why the cancellations happen. If it's finite, and it has to be crisp, it can't be some vague thing that, oh, there's some cancellations between diagrams. No, I have to have that reason.
Something like a symmetry.
Like a symmetry, I mean, we have someone deciding about the double copy structure. Maybe I could explain that with.
Let's do double copy non-perturbative. So in notice there are non-perturbative effects that are related to these divergent, not the divergence of the terms, but of the series. Do they have doubles? Well, that's about Euclidean solutions.
Instantons are self-dual theory.
Sorry?
Instantons are solutions to self-dual theory. There's some sort of a map of levels of self-dual theory.
Yeah, but that means that self-dual gravity has solutions, not ordinary gravity.
No.
Ordinary gravity.
I mean, there are instantons and there are Euclidean finite action solutions. Einstein's equation.
Well,
are they related to Euclidean finite actions of angles?
It's something I think it's worth looking into.
I asked you, and you said it should work. Then somebody said, how do we complexify that?
Yeah. Well, the null vector is, you need a null vector for the Kerr-Shield construction.
For obvious, that you need a perturbation about Minkowski space.
But you just need a null vector for it to work, right? You need a vector that's
for banish because k squared equals 0. It's just algebra.
Yeah, I guess. I mean, the self-dual story. I mean, in principle, just works in Euclidean space as well. Right? I mean, if you just forget the Kerr-Shield stuff. I know other ways of doing self-dual. There's these equations.
So if I take the self-dual Einstein equations in Euclidean space, are those solutions also Euclidean solutions of the regular Einstein equation?
Yeah, in the usual way. Yeah,
Okay. So there's your answer.
What?
He's got examples.
Well, in principle, examples can be constructed. We haven't actually done that. One thing I haven't done is taken, an instanton that we all know and love, and converted it into this gauge where I can see the map between the equations. And
but you're arguing that it's going to work.
This is something you can go ahead and do.
You're arguing that it's going to work.
Yeah, well,
if you look at the Einstein solution, the way it left constructed, it looks very similar to things you used.
In this example that you gave, the relation between the self-dual equations, I mean, was there an algorithm for going from one solution to the other, or were you just saying that the equations look similar if you replace the structure constants by the structure constants of this order algebra?
Well, I mean, in words, you can see that what you're supposed to do somehow is change the bracket with this other bracket. Yeah, if you give me some solution, actually ask me to do it. I think you can probably do it, but you have to get into
There's this
it's not that there's a map between the solutions that there was for the Kerr-Shield.
I don't know. Yeah, I imagine you probably did.
In a regular instanton, there's this map between the rotation group in space and the rotation group in group space. So you probably have to have some analog of that.
But the structure of gravitational instantons are very different to the structure of instantons. Yeah, I mean, the moduli space is well, yeah, I mean, you've got a hypercare moduli space for the gravitational instantons. Yeah, the moduli space is very different structure.
But the action should be some area, right?
But
there's something on this
Schwarzschild and
so in the end,
Mills instant and torsion or both dipoles is.
Well, the squash shell is very three-dimensional, isn't it? But the time-like symmetry, whereas the basic instanton Campbell's instanton is very much a four-dimensional object. So, and that actually persists throughout the instanton story. The gravitational ones have a three-dimensional character. Gibbons Hawking, gravitons rule. Well, the other ones don't. And they're AOE. They're not. There's nothing on the core sphere except for ground metric.
So there are constraint instructions for both the ALEs and the instanton.
Yeah.
But they're different. They're not very.
Yeah, that's right. I mean, they don't connect very well at all. I mean, they have a family resemblance, but I mean, there isn't really an obvious map from. I think there can be parameters in
By the way, if people want to see that, I can actually offer some insight where the cancellations come from in gravity. They're actually related to cancellations that happen in Yang-Mills theory. There's ultraviolet cancellations that are in some sense well known in Yang-Mills theory. And you can import them into gravity. For ordinary Yang-Mills. Just give me we'll take 1 minute. Well, more than a minute, but not very long. So, if I write down, let's just do one loop. So if I write down a Yang-Mills amplitude, I can write it in terms of 3 color structures. Let's call it C1, 2, 3. So this is just using what's called the color decomposition, where we just decompose it into the 3 color factors where you dress with FABCs. And it's the 3 different permutations. So it's 1, 2, 3, 4 plus C 1, 4, 3, 2, and the next channel 1, 3. I think I moved something. Oops. Okay, it'll just take 1 second to. Oh, this one is 1, 3. Okay, and I've done nothing here except what's called the color decomposition. So this is a general formula, and this would be true in pure Yang-Mills theory. Now, if you look at this object here, this is a color tensor that's a 1-loop color tensor. So in order to expose the divergences or the divergence properties, what you want to do is switch color basis into a basis that has C1, 2, 3, 4, and then it has 2 other elements in it, CA. So that's just the tree color tensor. And then in the other channel, this is CA. Just the quadratic chasm, 1, 2, 3, 4. 1, 2, 3, 4. So you just want to change the basis. So it's just a little bit of color algebra. And if you do that, what you find is that the expression can be written as 1, 2, 3, 4, A 1, 2, 3, 4 plus A 1, 3, 4, 2 plus A 1, 4, 2, 3. And then you might guess, let's call this thing T 1, 2, 3, 4 for the, and then A 1, 2, 3, 4 plus P, the other one. Maybe we'll call it 2, 3, 4, 1, A1. Anyway, times. Anyway, plus another tree object. Okay, now here's the key point. You see this tree color tensor? This loop color tensor. So this corresponds to this. So now, what do we know about Yang-Mills theory? We know it's renormalizable. If it's renormalizable, it means that
this cannot be divergent. The divergences must be in the tree color tensors. So that immediately tells me an identity. So renormalizability says that the divergent part, so it says that the divergent part of these partial amplitudes, 1, 2, 3, 4, and this is in Yang-Mills.
So what, I mean, that's only because you've done something with the quartic vertex.
No, it's just a point about the normalizability.
I understand. The counter term from here is canceled by the 4.
Well, the counter term, another way to say this is the counter term diagram. So the counter term diagram obviously is proportional to the tree color factor. So it's just a statement that if you do a color decomposition into tree part plus loop color, the loop color cannot contain a divergence.
If I hadn't known about these tricks of getting rid of the quartic, I would have said that.
This is just Jacobi identities were used. This is just pure color. All of this is color. So we're just organizing things according to color. There's no, there's no trickery. There's no BCJ has happened yet. BCJ is going to happen on the next line.
I heard about BCJ.
Yeah.
I was just talking about.
Yeah. So this is just a state. Okay, this you can do in Yang-Mills. You just do a color decomposition. So it's just color algebra. You organize things into 3 different color factors, and you can, by using the Jacobi identity over and over, you take all the color factors of these diagrams and you push them into these diagrams plus the permuted ones. That's where this formula comes from. Okay. And then there's one more step where you change the color basis to make it more obvious where the divergences are.
Are you saying that
All I'm saying is
counter
that
term can never reproduce the C1, 2, 3?
Yeah, the count, exactly, that's all I said.
The full answer
Yeah.
looks like something with a tree color factor
Right.
and a
And
finite
something
big
else.
amplitude.
Right.
And why isn't there this tree, the purple tree? With no
The 4 point, that guy has the same.
It's all absorbed.
That thing has the same, that's the same
Yeah.
color structure.
Yeah, you're right.
It's just FF.
Yeah, all of that.
He's saying that there's FF, which can have a divergence, and FFFF cannot have any.
Exactly. That's all I'm saying. So there's a color factor that cannot have a divergence in Yang-Mills, and that's just by the standard well-known principles of renormalizability. Right? There's nothing fancy here. Okay. But now let's look at this formula, the first formula, and let's apply the BCJ idea that we're going to change ordinary Yang-Mills into n equals 4 supergravity. And the way we do that, the way we do that is, what we do is we take C, 1, 2, 3, 4, and we change it into the numerator, 1, 2, 3, 4, of n equals 4 super Yang-Mills. And I happen to know offhand what that is because it's trivial. It's STA tree. And then it happens to be that this thing is completely crossing symmetric. Just by good fortune, that means all of those are the same. C, 1, 3, 4, 2, it goes to the same place, STA tree. I mean, those of you who know string theory will know this is the coefficient. This coefficient is what you find in front of string theory, and it has a crossing symmetry. But anyway, and then the last one is the same, 1, 4, 2, 3. Okay, it goes to STA tree. So that means this thing factors out in front when I turn it into supergravity. So immediately I write down n equals 4 supergravity, the 4 point, at one loop, is equal to STA tree. And then I have this combination 1, 2, 3, 4 plus 1, 3, 4, 2 plus 1, 4, 2, 3. Now, where have I seen that combination before? I've seen it right here as the coefficient of the color factor in the Yang-Mills. This cannot be divergent. So the divergent part is equal to 0. Okay, so that's how the gravity, n equals 4 supergravity, has inherited a cancellation that happens in Yang-Mills. Now, in gravity, you'd say this is magic, and I gave it a name. I said this is enhanced cancellations, right? So some fancy thing. But if we go back to the Yang-Mills, you see where it got inherited from something completely textbook, right? That's a normalizable theory. Now you can start playing this game in higher dimensions. We can go to d equals 6. D equals 6 has an f cubed, an f cubed operator is the divergence. F cubed, once again, lo and behold, the counter term is tree-like. Therefore, in d equals 6, the Yang-Mills cannot have a divergence in the loop color tensor. Therefore, let's just make this in d equals 4, and we can also make this in d equals 6. So it's also finite in d equals 6. Okay, now you might say, oh, that's pretty cool, but right now all I'm really doing is reproducing well-known things that were understood in the 70s. So in the 70s, people worked all this out, and there's no surprise here. Let's go to a place that's surprising. We'll go to 2 loops. So if we go to 2 loops, then luck is on our side, because the key trick to make this work is that when n equals 4 super Yang-Mills cannot depend on loop momentum. If it depends on loop momentum, I cannot make the relation very easily. I have to actually do some, the integrals change. But if it's independent of loop momentum, I'm good. I'm good to go. So it turns out, if you go to 2 loops, and now we're going to go to, let's say, d equals 5. If you open up the literature, you will find in d equals 5, q equals 16 supergravity, so that's half maximal supergravity. They'll tell you it has an arc to the 4th divergence. It's a valid counter term by all known symmetries. No one has as yet an explanation for this, but we have an explanation. The explanation is basically what I told you there. What you do is you do the double copy. You use the fact that the color factor, so let's call this 2-loop color factor, 1, 2, 3, 4. When you do the double copy, one of the copies is very simple. You go through exactly the same type of argument, which I'm not going to do on the blackboard. That's much more involved, but the basic idea is the same. You look at the Yang-Mills in d equals 5. Guess what it is? It's an f cubed divergence. F cubed divergence can only have a tree-like colored divergence, the divergence in the tree color tensor. It cannot have a divergence in the 2-loop color tensor. It cannot have a divergence in the 1-loop color tensor. So then what you do is you demand that be true. That gives you linear combinations between the partial amplitudes, just like we see at 1 loop. Some linear combination is equal to 0. You plug it into into the 16 supercharged supergravity, and you prove that it's finite. Right? So what that shows you is that the source, like here's the key thing, the source of magic or cancellation is old magic. It's the basic ideas that we understand about the renormalizability, or maybe not the normalizability, since this is non-renormalizable, but we understand gauge theory extremely well, and we know exactly where the divergences are and where they're not, and then you find that the supergravity inherits it. So now you might say, good, hey, that's great. Why don't you now prove that n equals 4 supergravity is finite at all loop orders, or n equals 8, or so on, by exactly this type of trickery. But the problem is that the key step for doing this is that when you make the color replacement to a numerator, it cannot depend on loop momentum. If it depends on loop momentum, the integrals are different from the ones you found in Yang-Mills. So then you can no longer analyze it. It becomes extremely hard. It doesn't mean it's not true. So the guess, or you could say the reason why I'm standing up here is I believe it works like this to all loop orders. It's just very hard to prove once you make substitutions that depend on loop momentum. Okay. So it was more than a minute, but not too much longer.
Go back to
yeah.
I wanted to go back to the connection between field equations and scattering. So it's kind of nice to see the well-known solutions of classical gravity coming out. But the one place we don't know what the field solutions of field equations are, or even what the equations are. All we have are amplitudes of string theory. So there we are, have amplitudes. Can we, from that, construct solution, or even equations? I mean, you said you could easily construct the Lagrangian, right? But all attempts to construct the Lagrangian, so-called string field theory, right, haven't proven particularly useful. So this would be a good place to start with the scattering amplitude, which historically used to be much simpler than field theory scattering amplitudes. And contained within them all this wisdom. I mean, everything you're learning, you continue to learn, is sort of there, from KKLT to the scattering equations, and this new stuff.
You added a K. It's not KKLT yet. Maybe someday they'll be related and everyone will be happy. Or unhappy, I'm not sure.
I was going to ask for the square root of the multiverse.
One where you only solve the hierarchy problem.
Maybe this raises a question which comes back to the earlier discussion of if we have the double copy amplitudes, why don't we have double copy solutions? So in string theory, we really just have nicely the on-shelf amplitudes.
Well, that's what amplitudes are. Right?
Yeah, so, well, and if we're going to try to do things like generate classical solutions along the lines, for example, I was just discussing putting in sources, then you probably really want off-shelf, right? So that's, and that's likewise a sort of a limitation for you guys, right? Or for the whole double copy story, or, well,
Our key limitation is that we don't have a constructive way of doing this. That's in a sense the key limitation.
Constructive
But
way of
anyway,
doing
get back to string theory, which is more interesting. The amplitudes there are finite, period. So the issue, for what it's worth, of whether this is finite or not, is obvious. The answer we all know, I think it's now, Ed must have more or less proven it previously. Perturbatively finite all orders. It is all of these properties you're discovering and
Well, the color,
I mean, I don't see anything.
the duality between the color and the kinematics is not.
Well, it is KLT.
Not exactly. No, not really.
Well,
or it's related. It's definitely related.
Whatever it is.
Well, I mean, surely it comes down to the factorization of the vertex operations.
That's right. It's certainly a loop level. I would say.
No, okay, loop level. You've got that other garbage, and you've got that whole bunch of our space stuff, which I agree that doesn't factorize.
Even at tree level, it's not completely trivial exactly.
No.
But these things are definitely related. There's no question. Right?
Tree level is closely related.
Yeah.
Essentially.
So,
yeah, I mean, it's
so
it's
I'm
not
just
optimized
concentrating all this incredible effort on field theories. I mean, N equals 4, I care about it. It's related to it. World closely, but N equals 8 supergravity. Oh my God. 30 years from now, it's going to be.
N equals 8 is a toy, and it's a good toy. It's a very powerful
for string theory?
No, it's a toy for understanding field theory.
Yeah, but
I don't know.
Anyway, what I'm suggesting is that some of these tools are ways of going might be useful for things like string theory, where in fact the perturbative answers are historically they were simple. They haven't been much explored.
People like Monferrat and Schlotterer and all who've been computing, Carlos Monferrat and Oliver Schlotterer and Stefan Stieberger, who have been starting to really seriously figure out where the analog magic is in string perturbation theory.
Just yesterday.
They're much more in the world of the DCJ direction than in the DCFW type direction, for example. I mean, things just come out much
There
before.
was a paper just yesterday, I think.
Yeah, they've done amazing. Carlos Mafra, well, sorry, Stefan Stieberger is the most senior person of the group, but yeah, it's Mafra, Stieberger, and Oliver Schluffer. And they have done very, very beautiful work, very, very beautiful work. Mostly using the pure splitter formalism, and figuring out how to completely systematically.
M-A-F-R-A, I think.
Yeah, and actually that they're, I think
what
that
did they find interesting?
Oh yeah, I mean, they have explicit tree-level amplitudes in superstring theory up to 8 points, 10 points. It's really
Two with 5 points.
and three-loop 4 point. They did Albany 2 years ago. So it's really spectacular work.
And it has a.
But it's very much in this world.
They have the structure. I mean, they use heavily these relations between the color factors and numerators. They adjust it so that their numerator factors in the full string theory actually do satisfy relations like that.
It's actually really, really interesting because somehow I think they're somehow identifying what you would think of as in the field theory limit. It seems like, so if you took the field theory limit of the field theory degeneration of the field sheet, it somehow chunks of Feynman diagrams seem to want to come together into natural gauge invariant building blocks. And or natural building blocks, of course. There's there's something very interesting, but it's very much in this work.
Back on the non-perturbative question, well, we can think about instanons, but we have a major non-perturbative phenomenon staring us in the face that a lot of us have spent a lot of time thinking about, and that is what happens to a black hole when it evolves. That's the generic outcome of a high-energy collision. It's the generic high-energy sector of the theory. So, again, that's a place where, at least from the perturbative approach, as we were discussing, it looks like you're basically just running into a divergence of the perturbation expansion. And so, if one discovers a new symmetry, then great, maybe that'll help us. But if not, then we might ask, that question which I put up to be a little bit provocative: do we really care if gravity or supergravity is perturbative?
I don't think that, but the finiteness or not, I think it's what I said. It's the reason.
There's finding the symmetry. But if that's
whether
true,
it's symmetry or whatever it is.
But if that's true, don't you have enough information? Shouldn't you have enough information by now to find that?
If we were smarter. No, the problem is that we don't have a good example of this. So there was maybe one thing.
Why does it have to be a symmetry?
It doesn't have to be a symmetry. So, for example, this thing I showed you, up to 2 loops, we understand why the divergence cancels in d equals phi, half maximal supergravity, when other people don't understand it. We don't explain it in terms of symmetry. It's a relationship between 2 theories.
So
right?
we're generally a structure.
A structure, if you will. So it doesn't have to be a symmetry. Right? The unfortunate thing.
I mean, the answer might be that it's simply the low energy limit of string theory.
Well, then that would still be pretty good because naively it's not like that, as you know. I mean, the low energy limit, it has the same problem that we face. Individual diagrams are poorly behaved.
I mean, it's not the low energy limit of the string theory to all orders in the loop expansion. The string theory has other states, binding states and all kinds of stuff. And you try to compact it like that to 4 dimensions.
Right, but it's still.
The perturbation series changes at some order in M-plane, momentum over M-plane.
So the problem we're having.
So let's see. But that, you mean because of the Clifford convolution?
Coincident modes, winding modes, all kinds of stuff.
Yeah, so all the continuous symmetries are brought into discrete symmetries, so they can't be, they're just not the same.
Yeah. I mean, this procedure that Speaker and his collaborators are working out so far looks like it preserves all the contiguous symmetries to all orders that we expect so far. And that's something that string theory will never do.
Right. The reason why we don't have the answer to, this question of what exactly is behind it, so we have, I showed you some things, is the unfortunate fact is that we don't have a good example of this phenomenon. So one thing I didn't tell you when I was talking about n equals 4 supergravity or n equals 5 supergravity is if you look at the complexity of those expressions, they're very hard to digest because they're very much like QCD. So a QCD expression, because it's Yang-Mills times n equals 4 super Yang-Mills. So the Yang-Mills part is extremely complicated. We would like to have a better example. And the unfortunate thing is probably the simplest example is 5-loop n equals 8 supergravity, which we don't have yet. I think if we have that example, we'll be able to make a lot more progress. And we need a better toy or a better example of this phenomenon.
Maybe I can ask another version of Steve's question. I don't think. Well, I think there's a common sense about this. So the question is there anything nice and beautiful about the gravitational oscillator at incredibly high energies, where you make a black hole? So I think the conventional picture is some thermal crap that's just that's not going to be particularly beautiful or nice. Nothing analytic is going to be known about it. It's just some junky phenomenon in a dual theory and so on. But we don't know that it's true. You could say wild things like but there are other strange systems that seem random, like the statistics of the distribution of the zeros of the zeta function, which have, well, it's true, it's very interesting to know that they come from something called the zeta function. So I don't know if people have any sense about that, but I think it's somehow related. I think if there is some...
You want to see something?
Yeah, let's say 2 to 2. Yeah, let's say
2 to 2.
Even 2 to 2. Even 2 to 2. Even 2 to 2. Might we someday analytically, is there some analytic formula out there for the 2 to 2 black hole gravity scattering? I think most people would say no way in hell because you make this big black hole and it's just got this
2 to 2 black hole.
No, sorry, 2 to 2 scattering at all energies when the energies are way bigger than quantum.
With an intermediate black hole.
Yeah,
with something like it.
So we know it's getting exponentially small. We know it's getting exponentially small. No. Could it be that we know? Could it be that in fact it's not like burning coal, which does look like crap, right? But
so if I scatter 2 hydrogen, look at 2 hydrogen atoms scattered in pretty high energy,
right?
Much higher than the energy of a star, they don't produce a star. I mean, I'm not going to learn anything.
It's a tiny amplitude, but there is a characteristic.
That's the difference. But there's something different about gravity. There is something about different thing about gravity. But we know something about this. We know something about it qualitatively every time. We know that it gets. I agree. That's why I'm asking the question for exclusive ones. I mean, we can ask the same question for the 2 to n process, and then we all agree, yes, roughly it's thermal, there's subtle correlation, blah blah blah. Then you could elevate the question: might there be really a concrete theory for those subtle correlations? You don't have to rely on the existence of some. But we could bring it back down to a 2 to 2. I think if there is something magical about gravity we don't understand, it's very likely that we will know that it was a matrix.
I mean, you should be able to see the tree in the tree.
No, definitely not.
Yeah,
no, it's a ladder sum.
You got to sum up all those, if you have 2 to 2
but if we're talking about a classical phenomenon, so why do we need all those loops to understand the because of black hole?
Getting field theoretic solutions from some trees. Right. Except that you have to remove this energetic.
But you also do approximation. You're doing a Michael approximation.
Well, you need
But
the
I
sum.
will not use it. You have
They're using it's not conversion, so
I mean, forget black holes, orbits you can't see at tree level, so.
Yeah, you cannot see the orbit. You get deflection.
Yeah, because you get a deflection which grows until it becomes big, and there's Sommerfeld.
But in my opinion, one important aspect of the S-matrix calculation is that you get classical behavior as a subtle point approximation. And I would like to stress approximation. So you never really get a classical picture. In other words, you get the deflection angle. You can always ask, what is the cross section if I look at the different angle, and you don't find zero. So I think this one should bear in mind when applying too strictly classical reasoning.
Yeah, something
Like
semi-classical.
Semi-classical. Yeah,
Another question along these lines, which maybe has been discussed already, is is something about very concretely about black hole microstates sitting there in the full 2-to-2 amplitude if we knew it? You know, it's true at the level of, oh, maybe you discussed this all already before. But if we certainly know for ordinary field theories, we go underneath the cut on the second sheet, and we find holes, and maybe sitting there as we go down the Riemann staircase, we find
probably
holes.
we know exact 2-to-2.
That's what I'm saying. Exactly. That's what I'm asking. So
it's analogous in QCD. In QCD, if I use scatter gold nuclei, we try to flip a particle. The larger limit is like a black hole. Thermalize it, eventually. Actually, people have now, as you know, discovered that even in proton-to-proton scattering, they can see some of the events are really head-on, and they can actually see something which looks like a fluid. So first they did it for proton gold. Yeah. And they saw some. But even for PP, the claim is if you select the events, so you want to look at something like two-particle scattering exclusive, which is what you do. So you have to choose somehow the events very carefully. So that you pick out this very teeny signal that would correspond to
But this is again the difference with gravity. It's guaranteed to happen. Yeah. So for it's the difference with gravity. It's guaranteed to happen.
Should it contain
of
the microstates?
Suppose I take the path of coal and I probe it, by taking some response function to a local probe. Am I going to see anything besides thermodynamic behavior? And the answer is no. I mean, yeah, maybe if you wait 1,000, recurrence times, and you'll see a lot of stuff that tells you about the structure of levels. But
this is exactly why I'm asking the question. Because it's not obvious. It's not obvious.
I mean,
that gravity will be the same. And maybe it is, maybe it isn't. But it seems like.
I mean, why should gravity be different? If you believe it equilibrates, I mean, why should it be different than any other equilibrium system?
Because of negatives.
Let's put it differently. Let's ask in QCD. Suppose you scatter 2 pions in the larger limit, and you go to high energy. And you can construct this S-matrix element, elastic S-matrix. Would you see the Hagedorn spectrum of strings? In the analytic structure of your 2-to-2.
Large N. Large N, yeah. But listen, you hopefully.
Yes. It will not have degenerate. I mean, in actual it will be not and I'm asking, including
like in the large N expansion, you will see the spectrum, but that's because the coupling is weak.
So this is similar. Well,
coupling
black holes have a lifetime, which is but there they will be very dense. The spectrum will be stringent. microscopic. Not as much. Well, EWM is pretty big.
Yeah.
It's not as big as EWM square, but it's still big.
Well, probably you lose, you can't really see all the way up the, you can see the exponential growth star, but the states way up, you'll have a breakdown in perturbation theory because their width will be non-zero at finite end.
Yeah, at finite end, they will start to overlap and we'll see only a mess.
Right.
Continue.
Right. And there should be a certain point at any finite value of n in which you will fail to see that high part of the spectrum.
Finite end, yeah.
Anything else on that?
When is the dinner?
We have reservation 6:45, so we'll read it for 6:20.
It is about 5, but we could, if people have something else, they would bring it up, or we could adjourn if people are talking.
It's a long day.
It's been a long day.
It's been a long day. That was fun.
Yeah.
I mean, it would be really cool if you might imagine you like start turning on the string up, all the bulbs move to the side. And then you just keep going. I mean, maybe they have answer to some nice spots. Maybe they turn into the zero for the zeta functions. Maybe they turn to, they might have some, in other words, of course, the question will be a little bit. They might be randomly the answer to a spectacular question.
There's
I think that's smaller, which is what I'm thinking.
If you go way up the spectrum, it doesn't, the whole thing, every finite is totally integral. Right? We believe there's going to be some beautiful structure there, and it's going to work out in some degree. But you can see even completing order perturbation theory that the levels with energies of order n squared are completely crazy. That's Hongdu and Festuccia argued that 10 years ago or something.
In the context of?
In the context of
large
n.
Large n.
How do you define that? You just take large n.
How do you use already?
You take n 500 million, okay, and calculate the levels that are order n squared in the free theory. There are a huge number of them. They're all exactly degenerate. Now do second order perturbation theory, okay? You get some mixing matrix between all those degenerate levels, and these guys argue that that's going to be a random matrix, basically. So even at first order perturbation theory, I think the idea that the whole spectrum is integrable is not correct. And those are, of course, the states that when you go to strong coupling are responsible for the behavior of black holes. The integrable stuff is not important.
So from that perspective, there's nothing nice.
Right.
That's the only perspective.
I don't know. I think heat is nice. I think thermodynamics is the most beautiful theory in the world.
You're right now.
Well,
good to see you.
great seeing you too.